we're going to be doing this truss problem here. So the first step of any truss problem is to consider the entire truss. Okay, now trusses have to be supported by something, whether it's cables or other types of supports like pins, rollers, could be fixed on one end. Okay, so we need to consider the entire truss, and we're going to say the truss is static, so the sum of the external forces and moments about the entire truss must be 0. And from this, we're going to find those reaction forces. All right, so let's consider the entire truss here. So you should always draw a free body diagram. It will help you a lot. Okay. Right here at point C is a roller, so there could be a vertical force. I'm going to call F sub C. Over here at B, we have a pin, so there could be a vertical force. I'm going to call F sub B Y. And there could be a horizontal force. I'm going to call F sub B X. We have this load here. This length is 0.7, 2.4, 2.4. All right, so I'm going to take sum of the moments about point B, and I get FC times its perpendicular distance, 2.4, minus 35 times its perpendicular distance of 4.8, minus the 48 kilonewtons times its perpendicular distance of 0.7 is equal to 0. Solve that. I get FC is 84 kilonewtons. Okay. And I can do some of the forces in the X. So I get F sub Bx is negative 48 kilonewtons. And same thing for the Y direction. We already found FC, remember? So I can just plug that value in. I can solve for everything. And I get F sub B Y is minus 49 kilonewtons. Okay, so now what we are going to do is we are going to consider a point or a joint in the truss. So I'm actually going to start with joint B. The reason I'm starting with joint B is because there are two unknown forces that act on that joint, right? We have a tension from this member and a tension from this member. Those are the only two things, the only two forces on B that are unknown. So I can start with B, because I can write two static equations about B. That is, the sum of the forces in the X and Y must be equal to 0. In this example, I would not start with point C. You cannot start with point C, because we don't know this tension, or this tension. And we can only write two static equations about a point in 2D. And we have three unknowns, so we can't solve that, okay? At least right now. So what we're going to do is we're going to start with point B, write the static equations, sum of forces in the X and Y must equal 0. That'll allow us to find the tensions in this beam, those two beams. And once we have that, then we can move on to point C, right? Because we already previously solved for this tension when we looked at point B. So now, when we look at point C, the only two unknowns will be this tension and this tension. This one will be known from what we did at point B. Okay, so you start at a joint where there are only two unknowns, and then you kind of work your way through the truss until you find the tensions and compressions in all the members. Okay, similarly, I would not start at joint A. You can't, because there's three unknown tensions. Okay, you need to find one of those tensions first before you move on to A. All right, so let's draw the forces acting on joint B. Oops. So this is B. I have, let's see, F, so BY is negative 49, so downwards, magnitude 49 kilonewtons. I'm just going to omit the kilonewtons right now. And F sub BX, that is 48 in negative direction. And then I have that's point B. I have a tension from this member here, and I'm going to call that member tension BC, right? Because it's from member B to C. Okay. Now tension, remember, acts tangent to the cable, or kind of bar in this case, where it connects. Okay. So the tension is either going to be in this way or this way. However, tension in a bar, the force points towards the other point, right? So the tension at B from this member points towards the other point where the bar connects. So in this case, points towards C. The tension in this member, I'm going to call BA, right? It points from B to A. So the tension from this member acting at point B points to the other point the bar connects to, so in this case A. So from B to A. Okay. So we have a tension like that. I'm going to call this magnitude T BA. And this magnitude T BC. The tension in bar BC, the tension in bar BA. Okay, now I need to write force vectors. So what is this force vector? Well, it's purely in the positive direction. So it's pretty clear that the vector TBC is just its magnitude TBC, just without the vector, in the I hat direction and 0 in the J hat direction. Okay, how about this one? Well, remember, a force vector is just its magnitude times a unit vector with the same direction as that force vector. What is the direction of this force vector? Well, again, it's from B to A. So let's write out that vector. So the vector from B to A is 2.4 I hat plus 0.7 J hat. That's just given in the problem, right, by the distances here. Right. Takes me from B to A. So this vector has the same direction as this force vector, but this vector is not a unit vector. We can make it a unit vector by dividing by its own magnitude. So I divide by its own magnitude. Now this whole thing is a unit vector in the same direction as this force vector. So to write out the whole force vector, we multiply this unit vector by its magnitude, like the force vector's magnitude. Its magnitude is T sub BA, I'm calling it. So multiply it by TBA, and I get the vector TBA. So that little vector, little arrow hat. I can simplify all this. and I get this. Right. Magnitude, unit direction vector. Okay. So now, another way you could do this is by finding this angle and saying, hey, the x component of this force vector is its magnitude, or its hypotenuse right here, times cosine that angle. And then its vertical component here is just its magnitude, so this hypotenuse length, times the sine of that angle. Okay. Both ways are really the exact same. Okay, just some ways might be easier for you to think about. So now what I'm going to do is write some of the forces in, let's see, the y direction for point B. Going back up here, what forces act in the y direction at point B? Well, we have this negative 49, and then the y component from this force vector. These two forces are only in the x direction. Okay, so we have minus 49 plus the y component of this force vector, or the j hat component. That is this, so 0.28 times TBA. So plus TBA times 0.28. Set that equal to 0. I can solve for the tension. Remember, BA. I get that is equal to 175 kilonewtons. My tension I solved for it is positive, so that means the member is actually in tension. In your free body diagram, always assume the unknown member forces are in tension. Draw them as if they are in tension. And then later, when you solve for their tension, if you get a negative answer, that just means your direction was wrong, and it's actually in compression. But assume it is in tension, and if you do that, then when you get a positive answer, that will always represent tension. And if you get a negative answer, that will always represent compression. So draw your free body diagrams as if they are in tension, even if kind of intuitively you know it is not. Assume it's in tension, and then show later whether it is or isn't in tension. Okay, and I can do some of the forces in the x direction. What forces here act in the x direction? Well, we have a negative 48, TBC, and the x component of this vector. So we have negative 48, tension in BC, again, because that tension is only in the x direction, purely in the x direction. And then plus the x component, or the I hat component of that force vector, which is just 0.96 times TBA. Set that equal to 0. We already solved for the tension in BA. That's right here, 175. So we can plug that into that equation and then solve for the tension in BC. I get negative 120 kilonewtons. I get a negative answer, so that actually means it's 120 kilonewtons in compression. Okay. So now I have found the tensions in these two members. So what I can do now is I can look at point C. And how many unknown forces do we have at point C? We have tension here and a tension here. We also have a tension from this member, but that is known now. We just found that. Okay, so now we can look at point C. So let's draw all the forces on point C. Tension there, that is unknown. Tension there, that is unknown. We have the reaction force we solved for, 84 kilonewtons. We have a tension from that beam. Let's label these. CD and CA. Now this tension here, again, draw it as if it is in tension. Okay? So I drew it as if it was in tension, acting at point C. What member causes this tension? Well, it's this one here. I called member BC. What is the tension in member BC? Well, we previously found it to be negative 120. Okay? So I draw it as if it's in tension, and I label it. So this is negative 120. Okay. Let's do some of the forces in the x direction. We have positive T sub CD. And then this force is in the negative I hat direction, so it's minus. How strong is that force? Well, it's negative 120. So again, always assume it's in tension. Draw it as if it is in tension, even if it's not. Draw it as if it is in tension. Label its strength, negative 120. So this is in the negative direction, so that's where this minus comes from. Its strength we already found was negative 120. So it's put minus 120 there. And then set that equal to 0. So I have T sub CD minus 120. Okay. I can then solve for the tension in member CD, and I get negative 120 kilonewtons, or just 120 kilonewtons in compression. I can do some of the forces in the y direction here. I have a positive 84, and then a positive T sub CA. So I get tension in member CA is just negative 84 kilonewtons, or just 84 kilonewtons in compression. Okay, so going back up to our physical diagram here. We know this tension now at this tension, then we just solve for these two. So our only unknown right now is this one that we need to find. You can do that a few different ways. You can either look at point A, in which case you would only have one unknown tension. Okay? So you can solve it. It's 2 or less. You can also just look at point D, because there's also just one unknown tension. Okay? So I'm going to look at point D here. So let's draw the forces acting at point or joint D. So we have this external load here. We have a tension that bar, tension from this other bar. Again, draw them as if they were in tension. I already forgot. This load, 35 kilonewtons downwards. Draw these as if they were in tension. What causes this tension? Well, it's bar CD. What causes this tension? Well, it's bar AC. Okay. We previously found the tension in bar CD. We found it to be negative 120. It's minus 120. So it's minus 120 in this direction, or also just 120 in the rightward direction. Okay. We can write out this force vector. Again, it's magnitude times a vector with the same direction, but a unit vector. So if you look at the problem and do that, you'll see that that vector is minus 2.4 I hat plus 0.7 j hat. That has the same direction as this force vector, but it's not a unit vector, so we divide by its own magnitude, like that. And we multiply by the force's magnitude, and that's our force vector. Simplify. All right. Let's do some of the forces in the y direction. What forces act in the y direction? Well, we have a negative 35. And then just the y component of this force vector, or the j hat component of that force vector, that is equal to 0.28 times the tension in AC. So plus 0.28 times tension in AC, set that equal to 0. Solve for tension in AC. Looks like I get 84 kilonewtons. Yeah. All right. So now we have solved for all of the tensions and compressions in all of the members, okay? If we were to do some of the forces in the x direction with this, again, just because the direction whole thing with this is kind of weird. Right? So it's this vector is drawn in the negative I hat direction, so it's minus. What's its strength that we previously found? Well, it's negative 120. We previously solved for that. Previously solved for its tension. Right? So tension is in the negative I hat direction, but its tension is negative. So it's negative 120. Okay, and then plus the x component of this. Its x component is just the I hat component, so it's negative 0.96 times TAC. Negative 0.96 TAC. So that's how you would do the sum of the forces in the x about, I think it's point D here. Okay, we don't need that. That doesn't help us solve for this tension. I mean, you can solve this equation for the tension, or you could just do sum of the forces in the y direction if you think that's easier. All right, so to recap, we considered the whole truss, said the whole truss is static. So we drew a free body diagram of the entire truss. And don't forget the reactions. Right? Don't forget to draw those reaction forces on that truss. And then from the static equation, sum of the forces, sum of the moments equals 0 of the entire truss, we solve for those reaction forces. And then we looked at a joint where there was only two unknowns. We did sum of the forces into x and y to find those unknowns. And we looked at another point, which now has two unknowns. So it's solvable. Did sum of the forces into x and y. And we just kind of kept working our way through the truss until we solved all the tensions and compressions we need. Okay. So this method of finding those tensions and compressions is called the method of joints because, well, we look at individual joints where those members are pinned together.